Kenza Engineering have been manufacturing and installing ground source heat pumps since 1999. With over 2,500 complete systems manufactured so far, you can trust Kenza to deliver award-winning expertise and advice. In this video, you will learn how a ground source heat pump works. The purpose of a heat pump is to absorb low-grade heat in one place where it is plentiful, then to transport, concentrate and release it in another location where it can be used for space or water heating. The ground absorbs low-grade solar energy by means of direct sunlight and rain. This gives the ground a year-round temperature of around 8 to 12 degrees Celsius. But how can this low-grade heat be used to heat an entire building? A cold water antifreeze mix is pumped through the ground within a series of energy-absorbing pipes known as ground arrays. As heat naturally flows from warmer to cooler places, the antifreeze mix circulating around the array is constantly warmed by the ground's low-grade heat. Having increased in temperature, the antifreeze mixture is fed into a heat exchanger called the evaporator. Within the secondary sealed side of the evaporator heat exchanger is a refrigerant which acts as a heat transfer fluid. When the water antifreeze mixture enters the evaporator, the energy absorbed from the ground is transferred into the refrigerant, which begins to boil and turn into a gas. The refrigerant never physically mixes with the water antifreeze mixture. They are separated like sandwich layers by the plates of the heat exchanger, which permits the heat transfer. This gas is then fed into a compressor. The pressure of the refrigerant gas is increased in the compressor, which makes the gas temperature rise. The hot refrigerant gas then flows into a second heat exchanger called a condenser, which features an identical set of heat transfer plates. The condenser delivers water hot enough to serve the space heating system and, if required, the properties hot water needs. Having transferred its heat, the refrigerant gas reverts to a liquid. This liquid is then passed through an expansion valve at the end of the cycle to reduce its pressure and temperature, ready to commence the cycle all over again. Low-grade heat stored in the ground has been upgraded by the refrigeration process to deliver hot water. For each kilowatt consumed by the heat pump, 4 kilowatts of energy is generated, effectively meaning the cost per kilowatt hour is quartered.
As installers, it's not really necessary to know absolutely in detail what's going on inside the box. As an installer of a heat pump, you're probably more interested in the water connections and in the electrical connections. But what we found over time is installers who have a basic understanding of the refrigeration process that's going on inside this box find fault finding and diagnosis and explaining to customers what's going on, perhaps even explaining if a fault occurs, what's the cause of the problem. So the purpose of this little session is to try and tell you what goes on inside this box, what can go wrong, and given that the refrigeration process isn't really a black art, it's really quite simple physics and science that we hopefully can explain right now. So what's actually in the box? There's a number of key components. I'm going to just talk you through. We've got 2 water pumps. A load side water pump, which is your hot side, your hot water that's going to distribute around your house, and a ground side water pump, which is pumping the water around your ground arrays. I say water, in actual fact it's a mixture usually of ethylene glycol and water. It gives it some freeze protection. We've got an electrics box. Yeah, it looks complex. Most of its functionality is safety and temperature control. Really all it does in terms of operation is turn on and off 3 electric motors. 2 of those electric motors are in the water pumps. Let's forget about them. It's really not that important. Let's see what else we've got. This is the main component of the heat pump. This is the compressor. The bottom 2/3 of it is an electric motor. It's either on or off. In a Kenza heat pump, there's no variable speed. They just either run or don't run. The job of the electrics box is to decide when to run the motor. If there's a demand for heat and if the safety systems all say go, then the electrics box simply turns the motor on and off. Actually inside here, there's mostly electric motor, but in the top half is the scroll set. That's the pump, the gas pump that moves the gas around the system. I'm going to come back to the gas, but in terms of the working parts, this is the working components of a scroll set. This part in my right hand is fixed. The part in my left hand orbits, driven by the electric motor. It moves in a simple round and round mechanism. It's that lack of movement and that minimal action of the pump that makes the scroll compressor more efficient than other compressor types. We've got our 3 electric motors. What's left? Well, there's only really 2 other significant parts. Around on this side, we've got our heat exchanger sets. There are 2 heat exchangers, completely separate. There's never any possibility of water from one water circuit contaminating the other water circuit. They are entirely separate. It would take a double failure for water to pass from one side to the other. It really never happens. What the heat exchanger is a series of stack of plates. The heat exchanger gives you a big surface area for heat transfer between the water, or maybe the water and the glycol, and the refrigerant gas. We'll come back to the gas, but really all this does is condense something with a big surface area into a small compact little device. I've got one here that's sawn in half, and when it's in operation, if you could see inside it, it'll have a layer of water, a layer of gas, a layer of water, a layer of gas. And it gives you this big heat transfer area in a nice compact little unit. These never really go wrong. Because they're usually on sealed circuits, they don't suffer any deposits inside. The only thing that can actually kill them is if they get frozen with fresh water, and that's something as installers you need to take into account on your installations. It may be necessary to put a frost stat on the system if the heat pump is installed in an area where it could be subject to freezing. The other alternative is to put glycol in both water circuits, but you'd need to check compatibility with the underfloor heating system and the other system components. So inside this block we've got the 2 heat exchangers. They're actually mounted in like that. 2 separate ones. They perform quite different functions, but they're both just exactly the same heat exchangers. So the only other interesting components are the brass block, which is just here, and that we call the expansion valve. That controls the flow of refrigerant around the circuit. Here is a filter dryer assembly. This keeps the refrigerant system clean and it removes any moisture that might have got in there during manufacture. And that, as the main components of the heat pump, is about it. The refrigerant never gets used up, it never wears out. In fact, the only thing that can go wrong with the refrigerant is it's leaked out. So with an endless circuit, there's no obvious place to start or stop talking about what's going on with the refrigerant. But I think the easiest place to start is the discharge from the compressor. This is the outlet from the compressor. The compressor only ever sees gas, as in a vapor, whereas the refrigerant itself exists in 2 forms, both liquid and gas, vapor. We achieve the effect of pumping heat by repeatedly changing the refrigerant from a liquid to a vapor and back to a liquid again. The refrigerant is best likened to bottled gas. If you've got a bottle of gas that you use for a blowtorch or a stove, you'll know that when you shake the can you can hear there's liquid in it, but when you release the valve, vapor comes out. That's the magic, really, of a refrigerant gas. It has the same properties. It can be both a liquid or a vapor, and its state is controlled by its pressure. So by having a compressor working hard, fighting, if you like, the restriction of the expansion valve, we create 2 pressure states within the heat pump, a high pressure side and a low pressure side. Inside the high pressure side, which is the discharge side from the compressor, the gas comes out of this pipe here and passes into the condenser heat exchanger. It's held under high pressure in here by the restriction of the expansion valve and the pumping action of the compressor. With your bottle of camping gas or whatever it may be, when you open the valve, you're releasing the pressure. And what is actually happening inside that bottle is the liquid is changing state. It's boiling into a vapor. But that process is a two-way street. When they make the bottle of Caligas or whatever it is, they actually pump the gas in and the vapor condenses into a liquid. At that point, the bottles actually warm up. They have to cool the bottles. Also, you might have seen when you're drawing gas out of a bottle of calogas, the bottle gets cold. And that's the latent heat of change of state. The energy required for the gas to boil requires thermal energy, and we exploit that principle within the heat pump to transfer heat energy from our relatively cold groundwater circuit into our relatively warm underfloor heating circuit. So the gas in vapor form containing our heat energy, and I'll come back to why it's got the heat energy at the other end of the story, is discharged from the discharge pipe of the compressor and flows into our condenser heat exchanger. On a Kenza heat pump, that's always the left-hand heat exchangers. Here, on one side of the plate, we have our underfloor heating water, and on the other side of the plate, we have our hot gas held under pressure. So it's a bit like we're in the gas bottle filling plant. The gas is being pumped in at the top here, but as the gas travels down through the passageways in the heat exchanger, it gives off its heat into the underfloor heating water, and by the time we get to the bottom of the heat exchanger, the gas has turned into a pure liquid. It's a liquid condensed refrigerant. With the pumped action, the liquefied gas rises up the pipe, passes through the filter, which keeps it nice and clean. I'm going to turn this around. Passes through the filter, and it meets the restriction, which is the expansion valve. What the expansion valve does is it creates a little fight. It's holding back the flow of refrigerant that the compressor's trying to push through. That means that after the liquid passes through the expansion valve, it drops in pressure. The suction side of the compressor is directly connected through the heat exchanger to the outlet of the expansion valve. So this liquid refrigerant now, it's had the pressure released. It's like you've opened the valve on the camping gas bottle. And that, now what the refrigerant wants to do is boil, is change back to a vapor. But in order to perform that function, it's got to take in heat energy. It's got to take in thermal energy. We allow it that thermal energy, or we give it the required thermal energy by passing it through the heat exchanger of the ground side water. It's not very warm, but it's warm enough. This refrigerant has a boiling point of about -30 Celsius. Typically our ground temperature is +5 Celsius or somewhere around there. So it's plenty warm enough to boil the refrigerant back into a vapor. The water probably enters from the ground array at 5 degrees C, and when it comes to leave, it's probably down to about 0 degrees C. They're quite normal operating parameters. And our gas, which enters at the bottom as a liquid, emerges from the top of the heat exchanger, fully vaporized. Vaporized and containing the heat, containing the latent heat that's made it change its state. So although it's not warm to the touch, it's probably this pipe is only 3 or 4 degrees above freezing, it actually contains a lot of thermal energy. That gas passes back to the compressor on the larger diameter pipe and is drawn into the body of the compressor. Here it does another little useful function. It gets passed over the electric motor and cools the electric motor, so the motor has no requirement for any external cooling. It's purely internally cooled by the gas. So the gas is drawn back into the compressor, into the main body. By the time it reaches the scroll pump in the top, it's warmed up a little bit because it's absorbed the energy from the electric motor. It's warmed up a few degrees. So what we've done, we've picked up all the heat from the electric motor, so that energy isn't wasted, that becomes output energy. But the gas is still pretty cool at this point because it's low pressure. And probably the hardest thing for people to understand is, well, how does this cold gas become hot gas? But remember, the energy is in the gas. All we've got to do is squeeze it a bit. It's a bit like an old-fashioned bicycle pump. If you pull out the piston on a bicycle pump, it draws in air from the surround. If you hold your finger over the end of the bicycle pump and push the piston down, you squeeze that air down into a small space. And the effect of you're holding the end of the bicycle pump is it really gets quite hot. It gets really quite warm. The temperature rises. Why? Because you've taken air at a certain temperature, 20 degrees C say, and squeezed it down into a smaller volume. It's the same amount of heat energy squeezed into a smaller space. And that causes the temperature to rise because the same energy is just squeezed down into a smaller space. Well, it's exactly the same with the way the compressor handles the gas. The gas is probably 10 or 15 degrees C after it's passed over the motor. It enters the scroll set, the suction part of the compressor, and gets squeezed down, probably entering at about 50 psi in old money and exiting at about 250 psi. And that effect of that squeeze raises the temperature. It hasn't created the energy, it's purely concentrated, it's squeezed it. And that's why the discharge pipe from the compressor is probably up around 60 or 70 degrees Celsius. Most of that heat energy that's in there has come from the evaporation in the ground side heat exchanger. And that, of course, is where we started the story. That gas passes back into the condenser and off we go again, about every 45 seconds on a typical installation.